In this video, we're going to be talking about metering devices. Now, metering devices are considered a core component in the refrigeration system. So this video is a little bit long because we're going to be going through all the different types of metering devices that are currently available. So mechanical refrigeration and air conditioning equipment depends on a change of pressure as liquid refrigerant flows into the evaporator. Okay, we have to drop the pressure drastically from the high pressure liquid side to the low pressure evaporator side and suction side for the refrigerant to begin to boil off and absorb heat. There are many different types of mechanical and electromechanical devices that are used to create this pressure difference. These types of devices are called metering devices and are installed between the liquid line and the evaporator. A metering device provides a small opening or an orifice that allows a certain amount of refrigerant to flow at one time. As the system operates, the metering device limits the amount of refrigerant to pass through the evaporator. Since only a limited amount of refrigerant is allowed to pass through, the refrigerant is allowed to expand and is at a low pressure. There are different types of metering devices. The simplest of all metering devices is the capillary tube and the fixed metering devices. One of the more complex controls is the electronic expansion valve, which is controlled by a microprocessor. And just as a side note, you get what you pay for. So as you go up in metering device types, you will also go up in cost. The most common types of metering devices are the capillary tube, known as a cap tube, thermostatic expansion valve, otherwise known as a TXV, automatic expansion valve as an AXV, a metering orifice, sometimes known as a fixed orifice, an electronic expansion valve, known as an EEV, a low side float, LSF, or a high side float, HSF. And all of these have different purposes and types of equipment they're installed in. Fixed metering devices are the simplest type of metering device. They have a fixed diameter passage for which the refrigerant must pass through to enter the evaporator. They have very few to no moving parts. The main types of fixed metering devices are capillary tubes and metering orifices. Capillary tubes are used extensively in both refrigerators and window air conditioners, which is why we're talking about these in air conditioning. Metering orifices are used in heat pumps and split system air conditioning. Split system, condensers outside, evaporators inside. The rate of flow through a fixed metering device is relatively constant when the compressor is running. Metering devices that can change their orifice size to account for changes in cooling load are referred to as modulating metering devices. All types of expansion and float type valves fall under this category. They will self-adjust one way or another, and we'll talk more about that. Because of their ability to change refrigerant flow rates based on the load, they operate more efficiently than fixed metering devices. These valves are better suited for use in applications that is subject to frequent or extreme changes in cooling load. So let's start with the capillary tube. Capillary tubes are metering devices that consist of a seamless tubing with a very small and precisely formed inside diameter. This tube acts as a constant throttle on the refrigerant flow. The pressure decreases as the small diameter restricts the flow of liquid refrigerant through the tube. As the pressure drops, a small amount of liquid refrigerant starts to evaporate in the tube. The vapor that is produced by the drop in pressure is known as flash gas, and its formation provides a sudden drop in temperature in approximately the last quarter of the tube's length. So this is an example of capillary tube, and if you look really closely at the screen or at the picture here, you can see the little orifice where my mouse pointer is right now. Okay, these are very small tubes. The performance of a capillary tube depends on the following items: tube length, inside diameter, and the number of turns. The length, inside diameter, and number of turns in a cap tube determines how much pressure drops between the condenser and the evaporator. The longer the cap tube, the greater the pressure drop. The smaller the diameter, the lesser the pressure drop. Turns create friction as the refrigerant flows and creates additional pressure drop. Let's equivalent a cap tube to a garden hose, okay? Because that's basically what it is. You have high pressure liquid coming out of the spigot where the hose is connected to. If you have 25 foot of hose, that hose may create a pressure drop down to 75 psi at the end of the garden hose, and then it sprays out into a low pressure environment, becoming a very low pressure spray. If I make that hose longer, same inside diameter, same pressure coming into the hose, but now I have a 200 foot hose, that pressure drop caused by that restriction of the hose itself may be down to 25 psig by the time it comes to the outlet of the hose. Okay, a capillary tube and any expansion device basically is equivalent of the spray coming out of the end of the garden hose. So when we take then put this back in capillary tubes and actually look at the tubes itself, okay, if I have a 20-inch cap tube coming in at 170 psi on the liquid side, the outlet is at 20 psi, okay, I can be putting 2 pounds per minute of refrigerant through. If I have a 36-inch cap tube, again, same inlet pressure, same outlet pressure, but I can restrict down to 1.5 pounds per minute. So the length of the cap tube and the inside diameter of the bore makes a big difference. By the way, the inside diameter is called the bore diameter or bore size. In some applications, cap tubes serve the function of both the metering device and the liquid line. In such a case, it is connected between the evaporator and condenser. This is very frequent in window air conditioners. If the distance between the evaporator and liquid line or condenser is shorter than the required length of the cap tube, a portion of the cap tube may be coiled so that it fits. A fine filter or filter dryer is usually installed between the liquid line or condenser and the cap tube. The filter dryer helps prevent contaminants from entering and clogging the cap tube. It is very easy for a cap tube to be clogged. Even residue from your brazing, if you ever have to fix a leak in a system, can block a cap tube. It's very important that a filter dryer go in there. So again, we have our condenser, we have a filter dryer, and coming out of the filter dryer, we have a cap tube. Since it has to be a long cap tube, it's been coiled a couple times, and then it goes into the evaporator. Okay, we have to have that filter dryer in there before a cap tube. Cap tubes can be installed so that a portion of it is in contact with the suction line. This allows the two tubes to act as a heat exchanger in which the cap tube transfers some of its heat to the cooler suction line through conduction. The heat from the cap tube superheats the refrigerant in the suction line and subcools the refrigerant in the liquid line. So again, let's go back here. This area right here might be actually connected. Not where the refrigerant mixes, but just where it's soldered to the outside of the line. And this acts as a heat exchanger. Okay, and this shows it again as another picture. Okay, cap tube, suction line, so that there's a heat exchanger going on. We're subcooling the liquid in the cap tube, but we're also making sure that any liquid refrigerant that's in the suction line gets boiled off before it gets to the compressor. Remember, compressors are a vapor pump. They don't like liquid. Cap tube systems do not have check valves or directional control valves. They're used on small fractional horsepower hermetic compressor systems. Cap tubes must not have an overcharge of refrigerant. Severe frosting of the suction line during startup is an indicator of an overcharge. Cap tube systems and fixed orifice systems are what we call critically charged systems. They have to be charged to exactly what the manufacturer specification is. Now, if you do add a filter dryer to a cap tube system, and if that filter dryer is larger, you will have to adjust the refrigerant charge. And I believe on some of the certification tests out there, that is a test question. A metering orifice is a fixed orifice metering device that consists of a fitting with a small hole called an orifice between the fitting's inlet and outlet. A metering orifice is installed between the condenser and evaporator and provides a pressure drop between the high and low sides of the system. The metering orifice can be cleaned and removed. The orifice must be correctly sized to produce the proper pressure drop for a given system. The refrigerant charge is critical when dealing with this type of metering device. These are commonly found in package AC units and split systems. Occasionally, you will find an orifice attached when you purchase an evaporator or a condenser. You will find the correct orifice attached in a little plastic bag. You gotta put the orifice in. So one common type of metering orifice is used in the heat pump application. These metering devices are often called piston type metering devices. Okay, it meters in one direction and allows free flow in the other direction. Okay, so when the refrigerant is coming this way, okay, the metering device is pushed up against the passage and it forces all the refrigerant through the metering devices. When we have reverse flow, for example, in the heating mode, that metering device is pushed backwards and allows free flow of refrigerant around the orifice. So it's not metering. Piston type metering devices are bidirectional, but they have to be kept clean. These metering devices are installed between the condenser and evaporator coil. One metering device meters the refrigerant flow during cooling mode. The other metering device meters the refrigerant during heating mode. The TXV is a temperature actuated metering device. The valve mechanisms respond to load variations. The purpose is to keep the superheat of the evaporator coil constant. Again, TXV, thermostatic expansion valves. The purpose of this metering device is to keep the superheat of the evaporator coil constant. There's a bulb that is attached to the suction line after the evaporator coil outlet, that's evaporator outlet, and the bulb must be insulated and mounted on a horizontal section of line. The bulb cannot be installed at the bottom of the line, and I'll show you some pictures of this in a minute. Okay, so we have our TXV here and all of our internal components, which we'll get into, but there's a bulb with a cap tube that comes off of it. Has to be mounted at the evaporator outlet, as close to the evaporator outlet as you can get it. It's preferable to mount it on a horizontal section of line. You can mount it on a vertical section, but it's preferable to go horizontal, and it cannot be mounted on the bottom of the line because you do not want it to capture the temperature of any oil that's in that line. Picture of a thermostatic expansion valve with an external equalizer port. The sensing bulb senses the temperature at which the suction line and the force created by the gas in the bulb will open or close the valve. The fluid or gas inside the sensing bulb is called the charge. The gas inside the sensing bulb is not necessarily the refrigerant in the system. There should be no cross-contamination. TXVs use 4 types of charges. There's a liquid charge, has refrigerant that has the same pressure-temperature relationship as the system it's installed in. There's a cross-liquid charge that has a fluid that does not follow the temperature-pressure relationship. These are used in low-temperature applications. Sometimes there's a vapor charge, again, same temperature-pressure relationship, and then there's a cross vapor charge. Does not have the same temperature-pressure relationship. The TXV model number and part number will identify what replacement parts you need to use. The vapor charge is sometimes called a critically charged bulb. It has a small amount of liquid, mostly vapor. It's used for maximum operating pressure bulbs. You'll see these as MOP bulbs. It can only exert so much force on the diaphragm. In other words, once it's all expanded, it can't push the diaphragm open more than it can expand. Cross vapor charge is the same as vapor, but different temperature-pressure relationship than what's in the system. Okay, so when we look at the temp-pressure chart, we know that all substances have a temperature-pressure relationship. Okay, the refrigerant temperature-pressure characteristic is this line right here. It's that center line that goes up here. Okay, spring pressure and refrigerant pressure should follow. Okay, this is based on a cross-charged bulb. Follow that. The Sporlan cross-charge opening pressure is that chart right there. Again, does not necessarily, okay, follow the same temperature-pressure relationship. Inside the valve body of a TXV, there's a needle and a seat that is usually made of a hard metal such as a steel. The movement of these two parts creates the valve action. The seat is stationary and the needle moves as the valve. So again, when we take a look at that, if we pull apart a TXV, okay, we pull the nuts off the bottom and we pull it apart, we have a spring, we have a pin, and we have a seat, and we have the valve body itself. We have push rods that are connected to the thermostatic, the valve head or the bulb head, okay? This part is interchangeable. Okay, if these go bad, you usually replace the entire valve. So what happens inside is we have our liquid line coming in, and that needle forces down into the valve seat depending on the combination of the spring pressure and the bulb pressure. They're basically opposite forces. The spring pressure pushes up, the bulb pressure pushes down. If the spring pressure is greater than the bulb pressure, this will open. If the spring pressure is lower than the bulb pressure, this will force shut. Okay, and then that allows the refrigerant to spray out into the evaporator. The TXV is adjustable. Turning the adjustment counterclockwise sends more liquid into the coil, which reduces the superheat. Turning the adjustment clockwise chokes off the flow of liquid and increases the superheat. You need to do any adjustments very slowly and give the system time to respond. Okay, any changes to TXV are not fast changes. You make the adjustment, usually a quarter turn at a time. You wait 5 minutes to 10 minutes, let the evaporator even out, check your superheat, and then see if the change did what you needed it to do. The TXV starts in an equalized setting when you turn the system on, okay? Starts in an equalized setting with a 10-degree superheat, okay? So our bulb pressure and our spring pressure and our evaporator pressure, because there's pressure in the evaporator, are equal to each other. So it starts with a 10-degree superheat. As load conditions change, and heat is added to the conditioned space, the sensing bulb starts to warm up. The valve opens, and it allows more liquid into the evaporator. It lowers the superheat. Okay, so as the bulb heats up, it creates more pressure. It pushes down, and now the bulb pressure is greater than the spring pressure and evaporator pressure. The load on the evaporator goes up. As the load increases, the valve opens, increasing the flow of refrigerant to the coil. As the demand for cooling decreases, the bulb will cool off. The pressure-temperature relationship causes the pressure to go down against the diaphragm, and it closes the valve, decreases the flow of refrigerant, and raises the superheat. So now the load requirement drops, the evaporator cools, the valve will start to close because now the evaporator pressure and the spring pressure is greater than the bulb pressure. So it's pushing up on that seat. With newer evaporators, there's a pressure drop from the metering device to the suction line. Okay, the newer, very long evaporators, double wrapped sometimes. If the pressure drop exceeds 2.5 psi, a TXV with an internal equalizer line should be used. The external equalizer is used to compensate for the pressure drop from the inlet to the outlet of the evaporator. Distributors are the octopus-looking things that follow expansion valves on large multiple-pass evaporators. The distributors distribute the refrigerant through multiple passes. So we have our TXV, we have our liquid line coming in from the left side of this TXV at the top. We have our distributor that comes out, okay, of the TXV, and it distributes the refrigerant into different tubes of the evaporator. So if we look at it on an air conditioning system, okay, we have our liquid line coming in, our suction line coming out. We have our TXV here, doesn't matter if it's right side up or upside down. And then coming out of the TXV, we have a distributor that goes into the different passes of the coil. Now, usually, just as a side note, someplace in here, we will have a filter to protect that refrigerant, to protect that distributor. There might be a little sieve filter. Oh, here's the TXV bulb that will need to be mounted, okay, onto that suction line after it's brazed in. The rate of liquid through a TXV is directly proportional to the load conditions. The forces that control the TXV is the sensing bulb. This is a downward force that will open the valve. The evaporator pressure creates an upward force that will close the valve along with spring pressure. The spring pressure creates an upward force on the needle and helps close the TXV. The spring pressure is the only adjustable part. The TXV is designed to work at equilibrium. There are three factors that affect the capacity of the TXV: the evaporator pressure, or the evaporator temperature, the pressure drop across the valve, and the temperature of the liquid entering the valve. By adjusting the spring pressure, the superheat can be changed. TXVs can be internally or externally equalized. Internal has two lines. One is a liquid inlet, and the other is an evaporator port outlet. Externally equalized has three lines: the liquid line, the evaporator outlet, and the equalizer line. With externally equalized TXVs, the bulb must be mounted between the evaporator coil, outlet, and the equalizer line. You cannot mount on the compressor side of the equalizer line. The equalizer line must be as close to the compressor side as possible to ensure that 100% vapor is entering the quarter-inch line. Any liquid will cause improper TXV operation. You don't want liquid in the suction line anyways. External equalizers are used on large evaporator coils where there's a pressure drop. So when we're looking at a system that has an external equalized line and you're mounting the TXV bulb, it has to go between the evaporator coil and the external equalizer line. You cannot mount on the compressor side of the external equalizer. It will not work properly. And this is just a picture of the TXV with the equalizer fitting on it. Okay, you'll have your liquid line coming in from your condenser or receiver, most often in air conditioning, just condenser. You'll have your suction line to the evaporator, and then you'll have that third line that's just an equalizer fitting. The equalizer line will be connected into the suction line to assist the evaporator pressure, the upward force for proper operation. The sensing bulb must be between the equalizer line and the evaporator so no liquid can get into it. Externally equalized TXVs must be used when the pressure drop on an air conditioning system evaporator exceeds 3 psi. If a pressure drop on a commercial refrigeration system exceeds 2 psi, and a pressure drop on a low temperature system exceeds 1 psi. Those are your 3 guidelines. Now, when you install an air conditioning coil or an air conditioning air handler, you will see that you will see on the suction line, usually there's a brazed in equalizer fitting. It looks just like a Schrader valve fitting. Okay, and then right there, you will know if you need a TXV with an external equalizer. Most often in residential air conditioning and commercial air conditioning, yes, your TXV will have an external equalizer in the newer systems. Superheat adjustments, easy. TXVs are normally adjusted at the factory. When an improper superheat is suspected, first check the manufacturer's recommendation and check for all other obvious things before you adjust the TXV. Front setting the valve, turning it in, will starve the coil or increase the superheat. By front seating, we are turning clockwise. You put less refrigerant into the evaporator, your superheat will increase. Back seating the stem of the valve, turning it outwards, will flood the coil with additional refrigerant and will lower the superheat. Okay? What you're doing when you're turning it out counterclockwise, okay, you're actually allowing more refrigerant through, and it will do what we call flood the coil, allow more liquid into that coil. So clockwise shuts the liquid flow down. Counterclockwise allows more liquid in. The best place to get temperature reading is at the sensing bulb of the TXV. If you cannot access this point and the compressor has a long run to it, you can add 2 psi to your gauge reading. So convert the low side gauge to temperature. Okay, so we want the temperature of the evaporator. Okay, subtract that saturation temperature, that's the boiling point temperature from your gauges, from the suction line temperature near the sensing bulb. This is superheat. Okay, so you take your high side gauge pressure, convert it to temperature, and subtract the temperature of the suction line near the sensing bulb. This is superheat, sometimes known as evaporator superheat. It's very important to realize that it takes a few minutes for superheat to change. Do not make fast adjustments on these systems. When mounting the bulb, make sure the suction line area is clean for good heat transfer. If it's not, sand it. It should be secured tightly by at least 2 metal straps. It should be insulated. It should not be mounted under the pipe, as liquid refrigerant and oil can sit on it, causing incorrect readings. Okay. So, external equalizer on a small suction line, less than 3/4 inch, put it at the top. Okay. Again, metal clamps that are screwed on and clamped down tight. External equalizer on a large suction line over 7/8 inch. Okay, usually between at a 45-degree angle from the center line. Okay, someplace in there is fine. Do not mount them ever on the bottom of the pipe. Some TXVs are considered what we call maximum operating pressure TXVs, MOP TXVs. They place a limit on the evaporator's pressure to prevent the compressor from overheating. They do this by not opening fully under heavy load conditions. In other words, we're going to keep that evaporator cold. Dual port TXVs have 2 needles and seats that are in series. They're used in cases where a single TXV does not fit the specifications. Examples of this might be a beer cooler, where you may need a large amount of cooling for a short time when a new shipment arrives. then the cooler cools off and you need less of a load. You don't see the dual port TXVs in air conditioning that often. Okay, two TXVs, they're in series with each other. Balanced port TXVs are designed to operate in low ambient conditions where the head pressure, that's the liquid pressure, drops. The liquid pressure that opens the TXV is canceled out across a large needle. This TXV can also handle small amounts of vapor and flash gas. Okay, this is a balanced port TXV. TXVs will always on the head of them tell you what refrigerant it's designed for, and it will have a part number. Okay, you can cross-reference these numbers to tell you exactly what the type of the TXV will do. These are, so again, you'll see the different refrigerant colors. That's like R22, 134A, and I think that's 12. Okay, not in existence anymore, but you'll still see the TXVs out there. Now, let's shift gears a little bit and talk about the AEV, or the automatic expansion valves. Automatic expansion valves are known as an AEV, or a constant pressure valve. The AEV does the same thing as a cap tube does. It acts like a water valve. You don't see them as much as TXVs, and you rarely see them in air conditioning. But so we're still going to go ahead and go through this. The AEV responds to a load change exactly opposite from the TXV. As the load increases, the AEV will start to starve the evaporator, thus maintaining a pressure and boiling point. It's constant pressure. As the load drops, the AEV will begin to open and allow the pressure to remain constant as well as the boiling point. Okay, so again, we don't have a sensing bulb on an AEV because we're not worried about the temperature. We're worried about the pressures. That's all we're dealing with. So we have liquid refrigerant coming in. We have liquid and vapor coming out to our evaporator. We have spring pressure, and we have the pressure of the evaporator. So our spring pressure and our evaporator pressure are the two forces. The force that operates an AEV is the evaporator pressure. This is the upward force on the bottom of the diaphragm that tends to close the valve. When you front seat the valve on an AEV clockwise, you are opening the valve, which puts more liquid into the evaporator coil. Completely opposite from the TXV. Okay, remember, clockwise on a TXV, you're starving the coil. Clockwise on an AEV, you're opening the coil. When you backseat the valve on the AEV counterclockwise, you're starving the coil, which raises the superheat. Atmospheric and adjustable spring pressure exert a downward force that will open the valve. AEVs are designed to maintain a constant pressure in the evaporator. When checking AEVs, you rarely have a pressure port right next to the evaporator, and you need to add 2 psi to your readings to account for the pressure drop. Systems with AEVs and most systems with TXVs should have a receiver to ensure proper refrigerant flow to the valve. Okay, and this is on the refrigeration side. TXVs in air conditioning, split systems, rarely have a receiver. Okay, so just be aware of that. That TXVs on split systems, you won't see a receiver. TXVs on basically comfort cooling, you won't see receivers. Systems with a capillary tube will most likely never have a receiver. The receiver is a type of storage tank that holds extra refrigerant. So this is a picture of an automatic expansion valve. We have our inlet, we have our outlet. The direction does matter. Don't put them in backwards. We have the diaphragm housing, and we have an adjustable knob under the cap. Solid-state expansion valves replace the sensing bulb with a thermistor and the spring or diaphragm combination with a heat motor. The thermistor varies its resistance based on temperature. As this resistance varies, the voltage that is sent to the heat motor varies, thus opening and closing the valve. The thermistor is inserted into the vapor stream at the outlet of the evaporator. It will sense liquid in the line and close the metering device. This is an example of a solid-state valve and a thermistor. Okay, that thermistor actually screws into the suction line and is in direct contact with the suction vapor. If liquid touches it, it closes that valve. It protects the compressor. However, this requires some additional components, for example, a solid-state controller. Okay, so what we have, we have the sensor, we have a solid-state controlled expansion valve, we have bimetal wrapped with a resistance heater. We also have the step motor expansion valve. It's known as an electronic expansion valve, EEV. It uses a small motor to control the expansion valve's port. The step motor rotates a fraction of a degree for each signal sent by the controller. The controller remembers how many steps are taken and can return to a prior step at any time. The controller includes a microprocessor that is programmed with an algorithm that controls the motor based on a feedback loop with the thermistor. So this is a step motor expansion valve controller. You see terminal strips, you see solid-state controls, you have set points, you have a set point potentiometer that can be adjusted. So these are solid-state controls. This is the sensing element for that step motor expansion valve, or the EEV. The communication between the microprocessor, the step motor, the algorithm, and the sensor is considered a feedback loop. Same thing as we would find in a direct digital controller DDC system. So the sensor provides input to the controller. The controller controls the motor in the expansion valve. And this is a constant loop, For every change in sensor, the controller does something. So we are constantly using an electronics, which is very fast, to provide exacting control of the superheat in the system. So we have a set point and we have the actual temperature. The difference between those is the offset. So what happens is, as the actual temperature drops towards the set point, every time it drops, we do what we consider a reset. This is considered a reset. So over time, our actual temperature, we start off with this large curve, we get down to the temperature, and then we're constantly varying a little bit above and below that set point. EEVs are by far the most accurate expansion valves if they're installed properly. And people that are greatly worried about efficiency and about having close temperature to the set points, good temperature control, are going to use the EEVs. However, they are expensive. An EEV setup can run upwards of $400 or $500 at cost. Now, the low side float is an efficient and simple refrigeration control. Its job is to maintain a constant level of liquid refrigerant in the evaporator. Now, we say we don't want liquid in the evaporator. Well, we do have some systems out there that are known as flooded systems. Basically, the evaporator is a long cylinder. These are used more in refrigeration, so I'm not going to go into it heavily right now. But there's a low side float that when the liquid level of the refrigerant drops because it has boiled off, it allows more refrigerant to flow in from the liquid line. Oh, the suction line is always at the high point of this, so it doesn't suck liquid back into the compressor. Okay, high side float operation. Okay, we use the actual liquid side to keep the float operating. Okay, just the low side uses a float on the suction side. Okay, the high side uses a float in the liquid receiver. Don't see these that often, and don't worry too much about it for air conditioning, but it is a type of expansion device. So that takes care of talking about all the types of expansion devices. For air conditioning, you're going to see cap tubes in window units and small PTAC units. You're going to see fixed orifices in residential split systems, especially the older ones. You'll see the piston type metering devices in heat pumps. You'll see TXVs in just about every type of air conditioning system out there. TXVs right now are the primary manufacturer in high efficiency air conditioning and heat pumps.